All right, welcome back everyone from the break. And for our next talk, we have Benjamin, who will tell us about an efficient quantum algorithm for Heisenberg spin chains. Please take it away.
All right, thanks so much. I'm going to be talking about some joint work with Sergey, with David, with Calvin, and it's about algorithms for quantum spin systems. So let's just get back to the setting of quantum spin systems. You're going to have n qubits. And we're going to consider local interactions. This picture kind of has arrows as spins, and then each blob is kind of an interaction. And these mathematical models let us study thermal properties of these systems. Okay? So just to put it in math, you're usually going to think about a Hamiltonian, which is a Hermitian operator, where each interaction includes only a constant number of qubits. So in the case of this drawing, it's just 3. As a concrete example of that is this Ising model. So we consider a graph G. And the edges are the qubits which are interacting. And then I also have this, which gives rise to this 2 local term with the 2 z's. And then this other term, this 1 local term, is just, you should think of it as like a magnetic field that all these qubits are in. And since this Hamiltonian is diagonal, it's a classical system. Now we should think, like, what do we want to compute? Like I said, we're going to study the thermal properties. And the main question we're interested in is the ground energy. So that is just the minimum eigenvalue. You usually want to compute it to additive error in epsilon. Okay. And then there's this second task we're interested in, is when I have a quantum computer, now I want to prepare this ground state, actually. And you can see that if you can do goal 2, then you can do goal 1 by just measuring the energy. Okay. So now we can go back to our classical example and answer both of these questions. I'm going to give you some specific settings for the interactions. So here's the first example. I've removed the magnetic field and then just set all of the j's equal to -1. And this example is really great because we can compute everything about it. So let me just look at a single term. And the spectrum, you can see the -1 terms, which will give us lower energy and hence get us closer to the ground state. The spins have to be anti-aligned, 0, 1, or 1, 0. And when they're aligned, you get +1, which is not good for becoming the ground state. So this is called the antiferromagnetic case when this happens. And you can see the ground state is actually the max cut. And this is not like a polynomial time reduction to max cut. This actually just is the max cut problem. So we don't really have hope for a quantum or a classical algorithm of estimating this efficiently, given that it's NP complete. At least the decision version of this optimization problem. Okay. What about another setting where I now have negative terms on the z? Well, now I favor alignment. And this is really an easy setting. The ground states are just all 0s and all 1s. Right? Because each local term, I get the -1 out. That's as good as I can possibly do. And also, if we add a magnetic field now, we could get rid of this degeneracy. And since we're going to talk about quantum adiabatic evolution, we're going to need to compute a spectral gap. We're going to need to get rid of this degeneracy. So this magnetic field term is going to come back again and again. So just as a picture of these classical models, you can see that their difficulty range kind of goes from this easy ferromagnetic case all the way to this NP hard case. Okay? And I'm going to make a bigger picture later with quantum models. And now I'm just going to talk to you about what quantum models emit efficient algorithms. And this is going to be a classical simulation. So the first one is this ferromagnetic XY model. The Hamiltonian is actually just there for interest. If you're not maybe specialized to this field, then you can kind of just think of this as just another model of quantum magnetism. It's called the XY model because the 2 local terms have x's and y's. And again, I'm going to consider a ferromagnetic case because I actually want to compute things, so I need to be in this easy case that's not as hard as max cut. And for us, that's when the x terms dominate. Then we are sign problem free or stochastic, or in the easy case, and there's an efficient Markov chain Monte Carlo algorithm for this model. Okay. And then you might also ask about preparing the quantum, the ground state. Well, if you're in the case with the balanced J and Y, X and Y terms, then you can do that. I think that this is just a technical condition that could be removed with a little bit more effort. Okay, that's the first class of classically simulable Hamiltonians. This next one is this anisotropic XXZ model. And in the naming of these, the number of x's is how many terms have the same coefficient. So you can see x and y have the same coefficient, so I can call it xx. If they all three had the same, it would be the xxx. If just one had the same coefficient, it would be called xyz. But again here, I'm going to want the z terms to be dominant. And there's a polynomial interpolation algorithm for this model from Haro, Mehraban, and Soleil Manafar. This is a really great paper that we take a lot of inspiration from. And the technical thing that lets them get this efficient algorithm is that the partition function has a large zero-free radius in terms of the magnetic field, and also that this Hamiltonian commutes with the Hamming-Wave operator. Those are two technical properties that they need for their efficient algorithm. Formerly, it was unknown whether these ground states could be prepared, but I'll say more on that when we get into our results. The last class I'm going to talk about is these entanglement maximizing Hamiltonians. And this first one is, it comes from physics. It's been studied for, I think, over 100 years now, but it's the Heisenberg antiferromagnet. And each term, you want to maximize how much singlet type entanglement you have. And it's QMA hard, so we have no hope for algorithms for this problem. Okay? The other one is with EPR terms, where you want to maximize Bell type entanglement of this EPR type. And it's currently unknown whether efficient classical algorithms exist to compute the ground state of this easier problem. And then another note is that on bipartite graphs, these models, their difficulty is the same. You can just do kind of this single qubit rotation on half of the bipartition. But since we don't have algorithms for these, we can ask about approximation algorithms. And indeed, there's been a lot of work in recent years. You should read this table. Like the hard problem is the one on the left. This is QMA complete, so much more difficult. This EPR Hamiltonian is stochastic, or sign problem free, so it's an easier problem. And the numbers are the approximation ratios. So that's just how good is my approximation divided by the true answer. Okay. And in our work, we actually push this to 1. We get an exact algorithm for the EPR Hamiltonian, and hence the quantum max cut on bipartite graphs. Okay. So what we get is an adiabatic algorithm for preparing these ground states on a quantum computer. So now we're out of the world of classical approximation and into quantum approximation algorithms. And we don't just get the EPR Hamiltonian and quantum max cut on bipartite graphs, but yeah, question?
You mentioned a lot of examples in the beginning. I just want to ask whether the Hamiltonian in your results is still stochastic and have an efficient classical algorithm or not?
Yeah, so this one that I mentioned here is a stochastic example, but we get a very broad family of Hamiltonians, which include many non-stochastic Hamiltonians. And I'm going to comment on that in some detail. But yeah, that's the question to ask. Yeah?
When you say approximation ratio of 1, you mean literally exact? Or like
you give me an epsilon, and then I'll give you back the thing.
Okay.
This is what they call an exact algorithm, which I don't know if that's a very good name, but that's what we have. Okay, more questions? Yeah?
So the bipartite is what makes it
Yeah, exactly. So quantum max cut on any graph is this like QMA complete thing that you're never going to hope for. But on bipartite graphs, somehow that's enough structure to make it easier. Okay, I'm going to move on. Yeah, so this is the question of like, what models do we actually get? And you'll see this includes some non-stochastic models. This is the definition. So you have all 3 x, y, and z terms present. And then you're also allowed almost arbitrary magnetic fields. So the constraints we have are just that the z terms must be dominant. This is also some kind of ferromagnetic condition to avoid this NP completeness. And then the magnetic field in the z direction has to be dominant. And you should think of this as kind of lifting the degeneracy in the ground state. And just kind of a sanity check for these conditions is like, if I look at what are the classical models that are included in this class, they're all ferromagnetic with unique ground state. So in particular, like when there's no x and y terms in either the 2 local or 1 local terms, you get classical ferromagnets, which have alignment favoring and spectral gap. So it's kind of minimum requirements to say anything about these models. Now, since we've introduced this kind of fancier class of Hamiltonians, I can talk about a result in full generality. The quantum adiabatic algorithm is going to run in time polynomial in n, j, and epsilon inverse. J here is just the maximum field strength, okay? And you get an epsilon additive error estimate for the minimum eigenvalue. You do this just by preparing the ground state and then measuring. So I'll tell you why we're excited about this result, is it includes this previously unknown EPR Hamiltonian, which is equivalent to the Heisenberg antiferromagnet on bipartite graphs. And if you wanted to actually consider this ground state of this harder model, the antiferromagnet, it goes back to this beta ansatz from 1931 that got paths and cycles. And now we can do any bipartite graph, at least with access to a quantum computer. Another reason to be excited is that there are some problems with sign problems for which no efficient algorithms or heuristics are known. So maybe there's some quantum advantage. This is still very early. I guess we posted this to arXiv last week. So it's not exactly a very robust and long-lasting advantage proposal. And it's also kind of an example of this efficient adiabatic algorithm. And this is a very natural setting and proposal for quantum algorithms for which it is rarely the case that you can prove something rigorous about. So hopefully we can get more adiabatic algorithms in the future, maybe using extensions of techniques that we have. So I have some more things. That's kind of why we're excited. And then I have some technical notes. The main requirements for this is to find an adiabatic path, starting from a simple Hamiltonian at s equals 0, going to the target Hamiltonian at s equals 1, where every Hamiltonian along the path has a spectral gap, okay? This is kind of the thing you need to prove. And the proof is going to use these Lie-Yang tensors. So the Gibbs state of the Hamiltonian will have a large zero-free region in its generating polynomial. And I will define all of these things later. Last week as well, Takahashi and Ryudu posted to arXiv an extremely similar result on Tuesday. And their proof is, I guess I'll comment about what's the same and what's different. Their proof is using physics techniques, is much longer, and their spectral gap is slightly smaller. It's 8 times smaller. And they also have a restriction on the one local terms that we don't have. But I still think it's very interesting to learn their proof because it aligns more with how Markov chain Monte Carlo practitioners think about these problems. So let's talk about this big question, is a quantum advantage proposal. Here is kind of a picture of the landscape of quantum spin systems where I've put all of the examples that I talked about on this picture. And usually, when you want to look for quantum advantage, you want to exit this purple bubble of sign problem-free models and get out of there. So you can see the Suzuki-Fisher class breaks out of this sign problem-free area. But we also know that you shouldn't look for advantage in all of these non-sign problem-free models because, for example, this XXZ model from Haro, Mehrabad, and Soleimanifar can be efficiently computed. Okay, so here's the actual comment on sign problem freeness. When you satisfy this condition of all the off diagonals are non-positive, you get a Markov chain Monte Carlo algorithm. So this is why when you talk about not having the sign problem, you think it might be simulable. It's not necessarily the case that it's efficient, but in at least the physics world and the heuristic world, yeah, John?
So you gave like I guess the runtime for estimating the minimum eigenvalue,
Yeah, that's right.
If I just wanted to actually produce the state itself, let's say to error delta, like what is the dependence on the delta?
To error
Is
delta?
it also like a
Yeah, it's just 1 over delta.
It's not like a log 1 over delta.
As far as I know, it's just 1 over delta. Yeah. Okay. Yeah, but so they admit these Markov chain algorithms, which people run without proof a lot, and they learn a lot, okay? So this example of the EPR Hamiltonian, it is stochastic, it does not have a sign problem, and people run big simulations of this, I think with 10 to the 5 or 10 to the 6 qubits but on very structured graphs like lattices. And many people conjecture kind of that the ground state problem, at least for the EPR Hamiltonian, is in BPP. So maybe not the strongest proposal for quantum advantage, but we also have a lot of effort in this direction with no algorithms. So it's not out of the question. I hope that maybe this work will spur somebody to actually give a rigorous proof that this is in BPP. But now what's more likely for quantum advantage is these non-stochastic systems. Okay, so here's an example of one that our algorithm covers. I don't know what you can do with this Hamiltonian other than conjecture that it might be hard, but you have EPR terms, except each term has a phase associated with it. And each edge in the graph, you're allowed to pick a different phase. So this puts you, far outside of this sign problem-free regime. And like we know, this is not sufficient for quantum advantage. For example, like you have this anisotropic XXZ model, and if you want to maybe go for a classical simulation algorithm, this Barvanach polynomial interpolation that Alex talked about yesterday is maybe a good candidate. But naively, it doesn't work. At least for me and my collaborators, we spent quite some time looking for classical algorithms. And then yesterday on the archive, there was this paper that said instead of looking for sign problem freeness, you should look for this non-vanishing geometric phase property if you want to go for an adiabatic advantage. And just based on the back of the envelope calculation, it looks like this phase-shifted EPR has the non-vanishing geometric phase, whereas anisotropic XXZ does not. So maybe this is a good reason to believe. Yeah, question?
I think your question. So you should use a model like a quantum easy by finding adequate paths. So how large is this gap? Is it constant or?
The gap is going to be constant. It's going to be constant in the magnetic field strength. If you don't have a magnetic field, you can just add in a small one that's 1 over poly. And the gap we also get is optimal, at least for our parameterization of the Hamiltonians. Okay. I guess maybe the rest of the talk is somewhat technical. It's about how this statement can actually be proved, but it might be a good time to stop for questions. Yeah?
Can you say more about this non-vanishing geometric phase?
Yeah, so what you're going to do is, maybe I can write it on the board. And again, this is something that I think appeared on the archive like yesterday, so I don't know it super well, but you want to look at the graph coming from your Hamiltonian, and you want to look at a walk on the graph coming from your Hamiltonian, and you want to look at the product of all the phases times this -1 times the L. And if this is just constant 1, then you have the vanishing geometric phase property. And if it's not constant, then you don't have it. And it's like highly related to stochastic, but not exactly the same. And the proposal of this paper was that you should look for this property rather than sign problem freeness.
Is it like if I was on like a simple lattice, like a square lattice or something, would it be like that there's like a flux if you like go around like a plaquette?
I'm actually not 100% sure, but I would be happy to discuss this later. Yeah. More questions before we proceed? Okay, well, I think we can talk about the actual proof of this. First, I'm going to introduce this class of Lie-Yang tensors. Then we're going to talk about the proof actually gives a relative spectral gap, and then we'll show how to convert this to an absolute spectral gap, which is what you need. And then I'll just say a few details about the actual adiabatic algorithm, including the path. And this picture is like what the zero set of a Lie-Yang tensor can look like. Like I said, they're going to be polynomials that have a big zero-free region, and then all these x's are the zeros. I mean, this is part of some of the numerics I did for this project, but anyways. The definition of Lie-Yang tensors, so they're going to be tensors with kind of entries labeled by bit strings. It's actually somewhat important that they're bit strings. For example, we don't know how to make this method work for like qdits. And I'm going to state it in this generality so that we can study states, operators, and channels all at once. So here's the actual definition. You take a complex tensor, And then you look at the generating polynomial, where this is, right, it has coefficients given by the entries of the tensor. And then we call it a Lie-Yang tensor with radius r if whenever all of the variables are in the unit disk, the whole polynomial is non-vanishing. Maybe, does anyone have a question about this? This is kind of like the definition. Yeah?
What kind of disk is it?
What kind of disk? I mean, it is it's the product for each variable of the unit disks in the complex plane. Right? That's the zero-free region we're looking for. Yeah?
Can you give a little bit intuition like how this will be used, like in home?
Yes. Here, why Lie-Yang tensors? So there's a few reasons. One is because once you have the zero-free property, you can apply a complex analysis on this region. In particular, there's a lot of theorems about these holomorphic functions. We're going to use the Schwartz lemma, the series expansion, and you can also take the log of something that's non-vanishing and quotients. Right? You can put them in the denominator, and then you can still get more holomorphic functions. So we're going to be using all of those. Well, I didn't put them all in the talk because it would be terrible to chat about it on slides, but we use all of these things. The other thing is that from this complex analysis, you can often get a Barvanach polynomial interpolation algorithm of the type that Alex talked about yesterday, and HMS and Alex's work. These are both great examples of, in quantum spin systems, how this can be used to get a rigorous algorithm. And the crux of these algorithms, if you forget, is that in order to approximate something like the partition function, I just only need to take a few Taylor series terms of the log of the function I'm going to approximate, and then after I exponentiate that approximation, I get a good approximation to the original function. The last thing is speculative. Well, it's semi-speculative. In the classical setting, there's a theorem by Chen, Liu, and Vigoda that says from a zero-free region, you get spectral independence and hence a spectral gap, and hence some kind of simplicity. I believe this also should hold for up to some corrections in the quantum setting, but that's just speculation. The origin of these things was in the 50s. Li and Yang used them to study the phase transitions in the classical Ising models, which we've saw. Okay? So in particular, there's a phase transition whenever there's some kind of discontinuity in the log of the partition function. And if you have a big zero-free region, that kind of discontinuity does not occur, and hence no phase transitions occur. As an example of a Lie-Yang tensor, the Bell state has Lie-Yang radius 1. I've written down the generating polynomial here, and you can just see kind of like if you wanted this to vanish, you would need to have, like you can't have them both be magnitude, both of these Z1, Z2 magnitudes strictly smaller than 1, because then you would, the 1 plus Z1 times Z2 would have a positive real part, hence not be 0. And so the question is like, how do we get a more useful example of a Lie-Yang tensor? Like this Bell state thing is probably not going to help me, but maybe if I have something crazy like this, it'll correspond to a more realistic quantum system. And the main theorem for them is this contraction lemma. It's very simple, yet very powerful. So if I contract two indices of a Lie-Yang tensor, and it has Lie-Yang radius r, then I still have Lie-Yang radius r. Okay. This was first given by Asano in 1970 to give a more elegant proof of the Lie-Yang theorem from the 50s, and then Ruel in the 10s gave like a one-page proof of this. It's like very nice, and Ruel's proof was even more general. But to see how this can help us, well, the generating polynomial of a tensor product is the product of the generating polynomials, right? So products of polynomials is great if I want to talk about non-vanishing, because if they vanish, then one of them must vanish. So the thing that you want to do is take a tensor product of Lie-Yang tensors, and then just contract some of the indices in this tensor product to get something more complicated. And there's also this Hurwitz theorem from complex analysis that says that kind of polynomial roots are like the limits in the roots commute. So if you take a sequence of Lie-Yang tensors, you get a Lie-Yang tensor, which will also, this is also important for us, is this sequence thing. Yeah.
Can you say what was the limit here?
Oh, like if you consider a limit of tensors, and each.
Oh, so you mean just like the cuff? I know you let the k go to infinity.
Yeah. Well, what you would have is like a more realistic set. Yeah, you could have k going to infinity, but more realistically, you will have k going into, like each time you add on a k, you'll also add on a contraction, and then this is the sequence that you consider.
Oh, I see.
Like, so there's another term, but there's more contraction. So now, right, why did we consider the Suzuki-Fisher Hamiltonian, and why are they named? Well, Suzuki and Fisher showed in 1971 that these are the Hamiltonians whose Gibbs states are Lie-Yang tensors with radius 1. Okay. And the proof is very elegant and uses this idea. So all you're going to do is just take the Gibbs state, trotterize it, and then after you trotterize, you look at which just single kind of two local interactions have this Lie-Yang property, and then apply Hurwitz's theorem and contraction lemma. Okay. These actually have a lot of, Lie-Yang tensors have like a lot of quantum information properties that we put out in this paper in February. And the current work I see as kind of a completion of that work. Somehow we like missed this really nice algorithm in our efforts to study these Lie-Yang tensors. Okay. Now I'm going to talk about this relative spectral gap and then the adiabatic algorithm, but maybe this is another good time to pause for questions. Yeah?
I think I missed the point, but how does the Lie-Yang tensor relate to the spectral gap?
Yeah, that's what we're going to prove here. And, well, prove that. I mean, there's, of course, a lot of details omitted, but I think if you want an intuitive picture, you should just look at these top two conditions of like those dominant ZZ terms. Those are going to give you kind of some concentration on alignment. And then when you also add positive Z fields, this is going to select just kind of one aligned state as special. So there's going to be a gap.
Here, this is thermal states. Sorry, I get a bit confused about. So this is something about thermal states, right? Like,
Yeah.
how does it relate to the spectral gap of that?
Yeah. So, yeah, that is yet to come. That's like the next session, is what that relates to. Yeah.
Maybe this is a bit too speculative, but I guess what do you mean by spectral independence in a quantum setting? Are you looking for like a result that links zero freeness to mixing for like quantum quantities or for like Lindblad elements?
Yeah, I mean, I think the most obvious question is to ask if there are models other than this ferromagnetic XY model that admit an provably efficient Markov chain Monte Carlo algorithm. That's the direction I would go in first. But if you want to chat about that, I would love to. Yeah.
I guess you defined your Lie-Yang tensors in sort of a way.
Yes.
But one of the nice things about Barbanach for computing position functions is it just cares about being local. Should I think of your, like, is there a more general definition that is more adiabatic?
No, we actually, we use this basis dependence in a lot of places, actually. Like, somehow the basis dependence is related to the fact that Suzuki-Fisher class is about ZZ and Z positive Z fields. I don't know if that answers the question a bit.
Yeah, I guess one would hope, like, I could choose, if I wanted to just a larger class of Hamiltonians, I'd have to change this. Give some way to change their recipe for choosing it.
No, I am interested in this direction of like a larger class of Hamiltonians, but our proof does use this specific basis dependence thing in a lot of ways. Yeah.
Is it kind of similar to like the basis dependence of stochasticity? Like,
Yeah. It's not too different from that. Yeah. Okay. More questions? Yeah. Okay. Yeah. Now we can talk about how the spectral gap actually comes up. In our February paper, we showed that if you were a positive semidefinite n-qubit operator with a Lie-Yang radius strictly greater than 1, then you had some spectral gap, okay? And the proof of this used reducing to the case of projectors by taking a big power of A, okay? And then this Lie-Yang property, one way that it comes in is that the projector has to have rank 1. Otherwise, if you could decompose it into a sum of more than 1 Lie-Yang tensors, you'd get these orthonormal Lie-Yang tensors that somehow are in the subspace of this maximal eigenspace. And that causes a contradiction because you can't have orthonormal Lie-Yang tensors, at least in that way, right? Because then you could contract them together and get 0. And now we want to ask, can we say anything about the size of the spectral gap? Okay, and the answer is yes. Not about the absolute gap, but we talk about the relative gap. Okay, so here's the new theorem from the paper. I would say this is the main technical result, and then the adiabatic algorithm as well as the other spectral gap follow from this. But if you're a positive semidefinite Lie-Yang tensor, then the relative spectral gap is bounded above by 1 over r squared, where r is the Lie-Yang radius. Okay. The next few slides are somewhat technical. They're going to be about like a sketch of how you actually do this computation. So maybe if you're like a little tired, then this is like the time to nap, and then at the very end we can chat more. But first, you just want to consider these first and second eigenvectors, okay? And then you want to consider this gap, this ratio function, okay? That is the quotient of the first by the second. And since this ground state, right, since the Suzuki-Fisher theorem applies at any temperature, the ground state tensor is also a Lie-Yang tensor, which means in particular when you take the quotient, it's non-vanishing on the disk, and then we can apply complex analysis to this ratio function on the disk. Also going to define just this relative gap as alpha, okay? And what you get from the complex analysis on the disk is a squeezing property. And for all of the non-zero inputs to this ratio function, they actually belong kind of in a scaled version of this disk. Okay? The next thing you need to do is kind of consider some parameters s and t that are in between r inverse and r. And you apply the squeezing property to both disks, and you derive this bound on the diameters that way. Okay. Then another piece of complex analysis is the Schwartz lemma, which you can apply to kind of the ratio function minus something that makes it 0 at 0 in order to apply this classical Schwartz lemma. And you get the second inequality. And again, I'm just like kind of waving most of the computational details under the rug, but they're actually not that bad, right? Our paper is like very short, and the proof of this is like less than a page. But all I need to do now that I've got the squeezing inequality and the Schwartz lemma inequality is I can just combine them to get this, and then wait, maybe my slide, the very bottom of my slide might be cut off. Anyways, doesn't matter. If I just set, like if I take the limit of s goes to r inverse and t goes to r, then I get the desired inequality, like this relative gap bounded by 1 over r squared. Okay. Now I have a few minutes to talk about this adiabatic quantum algorithm. Okay. And this is just like the adiabatic theorem. If a lot of you are probably familiar with it. Yeah.
I guess in the previous one you said that the Gibbs state of this class of Hamiltonians, these are like Lie-Yang tensors of radius 1.
Yeah.
How do these theorems,
Oh.
I guess, work?
Yeah, because now I need a. Oh well. Sorry, maybe I said the wrong thing. But this theorem, this relative gap theorem, you actually assume that the Lie-Yang radius is strictly greater than 1, and then when I want to apply it to Lie-Yang radius 1 things, I'm going to just conjugate by an operator that makes the Lie-Yang radius slightly larger.
Oh, I see.
And that perturbation is not going to destroy the gap too much. I do have slides commenting on that, but maybe perhaps I said the wrong thing. Yeah, but this is the adiabatic theorem, and it says that if you want to kind of transport your ground state from an easy Hamiltonian to a more complicated Hamiltonian, the time you need to do that is delta over g squared. And G is the spectral gap, the smallest spectral gap. And then delta is just kind of related to the Hamiltonian. And this delta is where that dependence in J comes up in our algorithm. But this G is kind of the big task. This is the thing that is like far harder to compute. And the delta just has to do with like how is time normalized, how is energy normalized in your Hamiltonian. And I guess we're going to answer this question now of like, how do I go from Liang radius 1 to strictly greater than 1? Well, I'm going to consider this Hamiltonian, where I've now added a uniform Z field. And I've taken the strength of the field to be mu, where mu is the minimum magnetic field strength in my original Hamiltonian. And this is, I've added the largest possible field that will not take me out of the Suzuki-Fisher class, okay? That's why I choose this, okay? And now, since I'm in the Suzuki-Fisher class, I have Liang radius 1 for this Gibbs state. And a really nice thing about the Liang property is that you can think of it qubit by qubit. So if I consider this A beta, that's this Gibbs state conjugated by this magnetic field operator, then I can just do this 1 qubit calculation, which tells me that I have a slightly larger Liang radius now. Okay. And because I have the slightly larger Liang radius, I can now use my relative gap theorem on this modified Gibbs state. Okay. And all I need to do now is take the log, apply Weil's inequality, and I get this gap of 2 mu, where mu is just comes from the Z field of the original Hamiltonian. So that's kind of how the absolute gap comes in. This is the adiabatic path we choose. You just interpolate from kind of a pure Z field Hamiltonian to the actual Hamiltonian you want. There's a small gap, delta, which is we take as epsilon over 2n. And the reason there is just because if you don't have any Z field, then we can still use our theorem. And the algorithm is extremely simple. You prepare h of 1, and then Weil's inequality ensures that the estimate is good. I've got just one final slide, and it's about future directions. These are not very specific, nuanced, and insightful open questions. They're kind of the big questions. If you want to talk about the more specifics, I'd be happy to chat offline. But the first question is about the other thermal properties about Hamiltonians. For example, the partition function and a quantum algorithm for preparing the Gibbs state. Second one about dequantization. So perhaps we can find classical algorithms for these thermal properties like ground state and partition function. The kind of techniques that have worked before, I've tried and they don't work, but maybe one of you can do it. Perhaps Alex could do it. And then the last one is also related to this question that Alex asked about a more general condition than this basis-dependent one. Is what are other kind of algebraic structures in the Hamiltonian that can admit efficient algorithms? Okay, and that's all I had to share today.
We have plenty of time for questions. Oh, yes.
I'm pretty interested in your first question. It's have you tried anything for prepared thermostates, or
Yeah, we have. Yeah, yeah. So in our previous paper from February, we have a algorithm for preparing thermal states but it has some severe caveats, for example, that make it non-efficient. You need to collect quasi-polynomial classical data about the system in order to apply Barvanach. But you can prepare these thermofield doubles. This adiabatic thing seems to maybe have some challenges, right? Because we only get information about a small part of the spectrum, whereas the thermal state includes the whole spectrum. But yeah.
So I'm curious, as far as I know, everything in the previous work that you mentioned is doing sum of squares stuff and then rounding.
Yeah, that's right.
Related things.
That's right.
And this seems just completely unrelated to any of that.
Yes, it is. Yeah.
Do you think there's any hope of of taking any ideas from your work and maybe using those to improve the kind of results, or do you think these are just kind of too analogous to
Well, I think even in this most recent result, I think they even proved an upper bound on what can be done with like these STP relaxation rounding algorithms. They might be too different, right? Because typically on these algorithms, you're going to do kind of some analysis on like the star graph, and then look at these like local circuits. Maybe you could imagine replacing these with like small like adiabatic paths and say something like that. But at least for these models, then I see no reason why you wouldn't just use this result, or maybe Anyways, that's kind of the thoughts. Alex, you had a question?
Sorry, can you go back to the adiabatic slide we were doing? I guess although you care about a ground state, you're like analyzing a Gibbs state.
Yeah, that's right.
Can you say more your intuition for this?
I mean, the Gibbs state is where the Liang radius lives, and
like you're taking beta to 0, not beta to infinity, so it's the backwards Gibbs state for looking at it.
Yeah, it is a backwards Gibbs state. I mean, yeah. Why? I mean, I guess the best intuition is just like the Gibbs state is what has the Liang radius, and that's the property we're going to use. I mean, the ground state I guess also has it, but I guess then the other I guess coming from the math is that like the relative gap, since you only get a relative gap, you need to take a log. So I'm just going to exponentiate so that I can take that log. But maybe from a more physics intuition of like relating the Gibbs state and the ground state, like why does that happen? I'm not sure.
Okay, any more questions? Okay, if not, then let's thank Benjamin again for the next talk. And we will have a lunch break now, so you can have lunch, and then we will meet again at 2 p.m.